Now, let us compute the variance of the standard normal random variable first. Okay? So remember, standard normal random variable is z, and we are interested in calculating the expected value of z square. And z here is normally distributed with location parameter 0 and scale parameter 1. So what is the expected value of z square? Remember, we need to solve the integral x squared times phi x from minus infinity to plus infinity for that. Now, 2 pages ago, we have determined that x squared phi x is equal to the second derivative of x plus the first derivative, the original function, not the first derivative, but the original function. So instead of writing this integrand here, I am going to replace it with the second derivative plus the function itself. And you know, the integral of the summations is equal to the summation of the integrals. So I separate this sum into 2 parts in integral. So we have the second derivative of phi x integrated. What would be the result of this integral? The first derivative, right? So the integral of the second derivative is the first derivative. Now we plug in minus infinity and plus infinity values to here, and we are going to get 0 in both cases because so the first derivative of x is equal to that. And if you plug in minus infinity and plus infinity in place of x, the density is going to converge to 0 very fast. It doesn't matter you have infinity values here, okay? So when you plug in infinity and minus infinity to this definite integral result, you would get 0 minus 0. And the second integral is what? It is the integral of phi x, which is supposed to be equal to 1 because that is the area under the PDF, right? And the area under the PDF is always equal to 1. So the result is 1. The expected value of z squared is 1. Remember, what is the variance of z? What is the variance of a standard normal random variable? Expected value of z squared minus square of the expectation, which is 1 minus 0 squared and 1. So the standard normal random variable has the variance equal to 1. Okay? Now, what if for any normal random variable? For any normal random variable, what would be the variance for any normal random variable? So what is the variance of a random variable with location parameter mu and scale parameter sigma? Remember now, we can generate a normal random variable by multiplying a standard normal random variable with a location scale parameter and adding the location parameter here. So instead of writing x here, I am going to write sigma times z plus mu, which is the inverse of the standardization operation. And according to our learnings in the end of chapter 4 again, the variance of a linear transformation is equal to what? The increment term vanishes. However, the multiplier term sigma gets out of the variance as a squared term. So it will be equal to sigma squared times variance z, which is equal to sigma squared times 1 here, which is equal to sigma squared. So here's the thing. The expected value of a normal random variable is equal to its location parameter, and the variance of a normal random variable is equal to the square of the scale parameter sigma, which is sigma squared. Okay? So the expected value is mu, and the variance is equal to sigma squared. Okay?